In this episode of Cosmic Sponge, digestive scientists construct a poop vault in order to save mankind's gut bacteria from extinction, while elsewhere, agricultural scientists promote insects over hamburgers at the drive-thru. And for our main topic, we look at the dangers of space travel after we pontificate on the impacts of our own individual food selections.
Well, that's funny. Look, I'm drinking out of a Burger King cup tonight. I guess I'm contributing to the demise of the gut bacteria.
I'm getting my I'm getting my butt bacteria drunk.
Yeah. Welcome to Cosmic Sponge, the podcast where we discuss weird wonders in the world. I'm Stephen Hall.
And I'm Jimmy Coe.
Tonight we are continuing our discussion about life out there in the universe and how difficult is space travel. Last week we discussed specifically, is there life beyond Earth? We talked about, is there a possibility of life in our solar system and out in the Milky Way and even beyond that to the vastness of the universe itself with all of the billions of other galaxies in the universe. Is life out there? And the truth is, we don't know. We've looked out using all of our instruments and telescopes and satellites and spacecraft and have yet to detect any alien civilizations or any kind of sign of alien life beyond Earth. And if we ever do discover that, even if it's a microbe, it will answer that question that life is not unique to Earth. Because right now, despite the odds, we don't know for sure. It could be. Or it could be life is all over the place and our civilization, our tool using intelligence to be able to even wonder about these sort of things and create the kind of technology to communicate with other civilizations. Maybe that's what's unique. So anyway, that's what we discussed last week. This week, we are looking specifically at the vastness of space. You know, our science fiction shows and novels make space travel look very easy. When you watch Star Wars or Star Trek, movies and television shows make traveling between the stars seem no more difficult than boarding an airplane and flying to Jamaica. The reality of it is that the distances are extremely vast, and there are laws of physics that can't be ignored when we want to look at the possibility of humans traveling among the stars, or even maybe aliens visiting us, as many people believe UFOs are. We are going to dive into all that. But first, Jimmy, what has been going on this past week?
Well, I took a moment to think a little bit about our last episode where we were talking about life amongst the stars. And then I thought, I wonder if there's life amongst my stomach. I was hungry. And lo and behold, there's critters in my stomach. I didn't know that. There's all kinds of little critters in there. And there are all kinds of bacteria and stuff, and they're doing their own thing down in there, which wigged me out a little bit. But then I found out it was more important than I thought. So important, in fact, that scientists have decided to freeze huge masses of poo in order to save mankind from extinction. I kid you not, poo from Peru and excrement from Ecuador. Now, I don't know what the difference between poo and excrement is, but I think they were trying to go for some kind of alliteration kind of feel. Poo, Peru, excrement, Ecuador. But
I get it.
They're being shipped to a top-secret facility that's been set up to ensure our delicate digestive systems aren't destroyed by modern life. So the Earth is currently in the middle of a mass extinction event, but the most endangered organisms aren't the mighty elephants or gigantic whales. It's the creatures living inside of my stomach. And there's some 30 trillion cells in the average human, but the microbiome consists of another 39 trillion microbial cells that include bacteria, viruses, and you probably didn't guess it, fungi. So one guy, Adrian Egli, director of the Institute of Medical Microbiology at the University of Zurich, is seeking to preserve human gut bacteria by freezing poo samples from all over the world in a unique archive, God, I hope it's unique, called the Microbiota Vault. And they've sort of modeled this after that seed vault. Yeah, that big seed bank that they have. And for folks out there that don't know, this seed bank is up in the permafrost. They dug this big old thing in the permafrost. I think they did it like in Sweden or Finland, Norway, something like that. And there's
Norway,
maybe one up in the Arctic Circle. I mean, there's several of them around the world, but basically they just get every kind of seed out there that they can, and they store it in this vault just in case we have like a nuclear holocaust or something, and then we have seeds there for the mutants that come up out of the ground after everything calms down, so they can reboot, I guess, agriculture.
Yeah, and it actually they're all over the place. It's not even that's one of them. It's probably the most famous one and maybe the largest. But there's seed vaults all over. That was started by I can't think. It was a Russian.
Oh, yeah,
scientist.
The project was inspired by the Svalbard Global Seed Vault.
Yeah.
Svalbard. You're right. That sounds Russian. It looks Russian. It's got like a lot of consonants and then maybe a couple of vowels in there on the edges.
Yeah, Svalbard. Yeah, that's the big one that you were talking about. That's in Norway.
Okay.
Yeah, actually with global warming, I think they're having issues with it. It's because
that's right.
Out there because it's so cold, but
yeah.
Down in the permafrost, but yeah, they've been having some problems with it. So, but this guy's putting together a poop bank.
Yeah.
So what's he going to do with all this crap?
See what you did there? I think he's just going to store it. Now, he's supposed to take it out like in 5 years. They're going to take some of the samples that they've already collected, thaw them out, and then sniff them to see if they still stink. I don't know. They'll run whatever tests that scientists run on poop to make sure that the microbes survive the freezing process.
How are they going to store all that shit?
I don't know.
Oh,
that's a good question. You got 1,000 of them. You could go on for days.
Well, that is important to our digestion is, the bacteria and other critters that live down in our intestines and everything. So, that's, I've always heard that's why when you take an antibiotic.
Yep, they say that in here.
You have trouble going to the bathroom, you may get constipated or whatever, because not only are you killing off the bacteria or whatever critters are making you sick, you're also killing off your gut bacteria as well.
Yeah, this article comes from the Daily Star, and it says in here that the widespread use of antibiotics, as well as the increasing consumption of fast food worldwide, is going a long way to disturb the delicate communities that exist inside of every one of us. So,
well, that's funny. Look, I'm drinking out of a Burger King cup tonight. I guess I'm contributing to the demise of the gut bacteria.
I'm getting my I'm getting my butt bacteria drunk.
Yeah. Well, I wonder. That's. I don't know if it's quite as vital as the seed bank, but maybe it is. What do I know?
This guy could be the one that saves us all with his poop vault.
Well, it's interesting you mentioned this, something to do with food, because I ran across an article on phys.org. I was looking at science news, and I was thinking about, maybe do an astronomy story because that's still one of my hobbies, even though I haven't been able to look through my telescope since November. I mean, I've missed all kinds of cool stuff that happened in December because it's either been raining like crazy or it's been zero like it was over Christmas or whatever. The night didn't work out because I had some other engagement. But I mean, back in October, November, I was out like 2 or 3 nights a week, really into it, and then suddenly the weather just didn't cooperate. Now, quickly, you got to tell us, your wife got a telescope for Christmas.
Yeah, let's phrase it that way.
To get out with it, yeah.
No, she hasn't opened it yet. It's still in the box. She's apprehensive.
Well, you're missing.
Yeah, I told her she doesn't care. she's
wintertime is your astronomy time.
Really. Yeah. She's reading all the books first, and she's just about ready to crack it out. She said that she read in the book that it's first gets a pair of binoculars and familiarize yourself with the night sky before you pull out your telescope. So she's listening to the book, and I was like, man, you're definitely not a guy. I'd be having that telescope out there and not even align it or anything. I just set it down and start moving it around.
That's what I did.
Yeah.
But yeah, I've heard that too. I actually bought one of the courses plus or whatever on astronomy and was watching it. And the first episode's like, well, you can just go out in the night sky and look up with your eyes, and which is true. And then of course he talks about using a pair of binoculars. I tried that before I got my telescope, but it just, I'm just not steady enough. I really couldn't, I couldn't really observe that well, especially some distant objects and stuff. I mean, it definitely magnifies it, but I just couldn't, you know what I mean? I couldn't relax and do it. But there is something to be said for that. The most fun I have with astronomy is I get out there and I pick a couple of targets during the day, set my stuff up in order to, okay, what am I going to need to do that, and kind of have a plan. Sometimes I'm maybe going to try and take photographs of something. But then, a lot of times I'm just out enjoying the night sky. I'll look through the telescope for a while, but then maybe I'll just look around, try and pick out constellations and stuff like that. So that's fun too.
Hey,
yeah.
How do we get off on the sidetrack? What were we talking
well,
about?
I just happened to think of your telescope.
Oh, yeah, not there yet. I can't wait till she breaks it out.
Yeah, Elizabeth's telescope.
Let's Elizabeth's telescope.
Well, anyway, I'm excited for you guys to give it a try. We can compare notes.
Sure.
So you had mentioned something to do with food. Oddly enough, the news story I brought has something to do with digestion, I suppose. But there's a couple of papers that were recently published from two different groups, two different pairs of researchers. Mm-hmm. They are trying to make the case for using insects as food for both humans and livestock.
Yeah, I've seen that.
They were both published in the Journal of Science.
Mm-mm. Yeah, I am not eating crickets without ketchup.
It's funny you said that. The article mentions crickets. A strong case can be made for using insects to meet the growing need for food around the world in the coming years, and also for using insects as feed for livestock. As the global population rises and the land available for growing more food becomes more scarce, scientists around the world have begun looking for alternative sources. In two papers in Science, the authors all agree that insects could provide the answer. In the first paper, the authors note that humans eating insects is not novel. People have been eating them for as long as there have been people, and many people in the world today still eat them. However, most do not. And in fact, in most places, people see eating insects as disgusting or even dirty. That could change, the authors argue, if insects were provided through commercially viable outlets. They note that eating insects can provide many nutritional benefits. Common crickets, for example, are very high in protein. That makes them competitive with meat from animals. The researchers also note that insects require fewer resources to raise than livestock, making them a prime green alternative. In another paper, these authors note that currently most livestock feed is made from fish meal and soybean meal. They also note that production of meat worldwide uses about 70 to 80% of all agricultural land and yet produces only about 25% of the protein consumed by humans. They suggest that replacing conventional feed with feed made from insects would free up large parcels of land now used to grow food for livestock. It would also be a healthier food source for animals. Also, farming insects is likely to become more feasible as the planet continues to warm. So what do you think? You ready to have some crickets?
Well, I don't think those scientists are reading the population data or the trends. So the world population's projected to nearly stop by 2100 and have less than 1% growth, which means basically not even replacement levels. So currently we're like 2.5, and the global fertility rate is expected to be 1.9 by 2100. So, actually by 2070, so not even by 2100. Yeah, I'm not too worried about that. I'm more worried about depopulation problems, and anybody who's looked into that, that's a really big problem. Most of the developed world is an upside down pyramid, which means there are more retirees than there are new people to replace them, and that's causing all kinds of havoc. Now, we're okay in the United States because we had a really big millennial generation, but Gen Z is pretty small. I don't need to eat crickets. Fertility rates are down too. So, I mean, they're attributing that, I think, to microplastics. I saw something on it. I haven't read the scientific material yet, but yeah, fertility rates are down too, worldwide.
Maybe that's it. Maybe that's the great filter we were talking about last week.
Yeah, could be. Or it could be the fact that people just start eating crickets and that causes them to be sterile. Who knows?
Maybe we're not eating enough.
Maybe
it's this Burger King fast food you were talking about, the dangers of killing my gut bacteria. Maybe that's it.
That's what it is. I haven't had fast food since 2020. But I've had a lot of crickets. I'd eat a cricket.
Yeah, good for you, man. You're going to live forever, right?
No, but I'm going to live longer than if I were eating that crap. At least that's what the doctor told me. I used to be a two Whoppers a day guy.
Yeah.
I love the Whoppers.
I miss that guy.
The guy that knew how to live. You know, it's that old story. If I were still eating those two Whoppers, it'd be the candle that burns brightest. I'd already be dead.
You know, I guess we should touch on the UFO paper. Do you have anything on that?
So they said that the reports from the military skyrocketed up to from 100 and some up to 500 sightings reported. And of the 366 of those new reports, of 366 new reports, so they're saying the 500 reports is a combination of the 144 previously compiled and then the new reports, which is another 366. Of those, 26 were determined to be drones. 163 were balloons. Balloons, people.
Love the balloons.
Yeah, I love the balloons. 6 aerial objects were attributed to clutter, and the remaining, they just didn't have enough information to put them into a category. So I guess they go into the UFO bucket.
UFOs.
They're UFOs.
Or flying saucers or whatever. And what we're talking about, people, since Jimmy just jumped right into the stats, but we're discussing the Pentagon's long-awaited report on unidentified aerial phenomenon, or UAPs. This is the annual report. This is they released the unclassified version of this report, and those were the stats that Jimmy was throwing out there. Yeah, in a nutshell, the report covers 510 cataloged UAP reports from agencies that were involved all over the world. I saw some feedback on this. One was Avi Loeb. We talk about him a lot, Harvard astronomer.
Yeah, it's different than astrology.
Yeah, right.
Right.
Sorry, Avi. Yeah, Avi Loeb, the Harvard astronomer, came to prominence whenever he suggested that it was possible the interstellar object Oumuamua may have been an interstellar spacecraft or probe of some type. But anyway, he says, a lot of people are asking for this data from the government. We want to know what you've seen, how you got these reports. But he's saying that scientists need to step up and try to gather this evidence themselves and not rely on the military or the government to provide it.
Right, and that's the point of the Galileo project, which we've talked about before, which I think Avi is heading. So, I don't know. We'll see.
Well, just like he said, and like I've heard many scientists say, I mean, it's worth looking into because, most likely the UAPs, the flying saucers, the UFOs are something logical. And especially these days, we have so many satellites being launched now. I mean, we have thousands and thousands of satellites. It's tripled the number of satellites that are in orbit just in the past 15 years.
Yeah, are they counting Starlink?
Yeah, Starlink.
There's a ton of those up there.
With all of that going on, I mean, there'll probably be, 10 or 15,000 satellites in another 5 or 6 years, as we have all these competing companies throwing them up there. But anyway, what I'm getting at is there probably is a logical explanation for many of the sightings, if not most of them. But if just one was an alien from another planet, it would be the most important discovery of the human race, wouldn't you say?
Oh, yeah, definitely. And, I know there's been at least one that is an alien that stopped by and said, "What are all these monkeys doing playing with those thermonuclear bombs?" What are they doing?
Shaved apes.
Shaved apes. Those Gillette apes.
But yeah, I mean, that's a good point. I know most scientists prefer to work in a field where they can look at the results of their experiment or whatever, but there's enough people looking into it. Maybe we'll figure something out. All right. You ready to move on to tonight's main topic?
Sure.
We really appreciate everyone tuning in and listening each and every week. But if you get a moment, please rate and review the podcast. It helps people find the show. Look for us on Facebook and Instagram. We also put this podcast out on YouTube in an audio format, but we may do video one of these days if I can ever get my little studio together. Go to our webpage, cosmicsponge.com. There you can find the web store and ways to support the show. Our contact information is firstcontact@cosmicsponge.com. All right, Jimmy, I guess we're going to be looking into the vastness of space, or even the half-vastness of space. So how about getting us kicked off tonight?
It was 1977, and while X-Wings were blowing up on the silver screen like Samsung phones before a full recall, NASA was busy launching 2 spacecraft of their own with far more success than Red 1. Voyager 2 launched on August 20th, and Voyager 1 2 weeks later on September 5th. It was a Goldilocks year, meaning a special alignment occurring once every 176 years provided a path of gravitational slingshots that assisted the probes and allowed them to visit a total of 4 planets: Jupiter, Saturn, Uranus, and Neptune. While Voyager 2 was the first to launch, it would be Voyager 1 that reached the edge of our solar system first, before entering interstellar space. Prior to that moment, it would discover a thin ring around Jupiter and 2 new Jovian moons, Thebe and Metis. Then it would discover a new ring around Saturn, the G-ring, bow chicky wow wow, and and 5 new moons. It was responsible for the famous pale blue dot photo, having turned and snapped a photo of Earth when it was about 3.7 billion miles from the sun. Then on August 25th, 2012, the first man to step on the moon, Neil Armstrong, passed away. It was on that same day that Voyager 1 entered interstellar space, continuing to provide critical information to this day on the hazards of space beyond our solar system, as it takes various measurements of cosmic radiation levels and interactions of charged particles from different stars in the interstellar medium. The Voyager probes remain the longest operational man-made spacecraft in human history, going 45 years strong as of 2022. In over 14,000 years, Voyager 1 will exit the Oort cloud, and in another 40,000 years, it will come within 1.7 light years of Gliese 445, an M-type main sequence star in the northern part of the constellation Camelopardalis, the giraffe. And if all this isn't good enough, both the Voyager probes also include a message to any curious alien out there in the form of a 12-inch copper disc containing music ranging from Chuck Berry to Mozart. Greetings are presented in 55 languages. A message from our peanut farming president, Jimmy Carter, kicks things off. Then there's the B-side, containing 115 images and 35 sounds ranging from whale songs to laughter, which just goes to show you that human ingenuity and 12 inches go a long way in space. Let's talk a little bit about... That's so stupid.
Oh.
Okay, let's talk a little bit about traversing the interstellar space and the challenges which lie ahead for mankind as we venture into the unknown. And I thought we'd kick things off by putting distances between planets and stars into like a meaningful perspective that we can really grab a hold of and understand.
Real quick on your introduction, did you say a copper disc? I thought it was a gold disc that was placed on the spacecraft. I believe it was a gold record.
Was it? Well, you know, we got the Google thing, so let's look at the Google thing. I had read it was a copper disc, but then I also read, and you corrected me early on, and you went ahead and edited that part out, that it was 5 planets that the Voyager mission visited, and it was really only 4. And it wasn't because Pluto wasn't a planet anymore. It's because the first thing to go to Pluto was New Horizons.
That's correct.
Yeah.
Yeah, and it did a flyby in 2014, I want to say.
Yeah.
Yeah, New Horizons was very fast probe, and but still took so long to get out there. And that's still an active mission, too. It also visited, one of the Kuiper Belt objects, I guess, one of the objects that are out there beyond the orbit of Pluto.
That's correct.
And I think they have it pointed at one more they plan to end that mission.
Yeah, I'm going directly to Jet Propulsion Laboratory for this. Pioneers 10 and 11, which preceded Voyager, both carried small metal plaques identifying their time and place of origin. And then NASA placed a more ambitious message aboard Voyager 1 and 2, a type of time capsule which we discussed. And you're right, It was a 12-inch gold-plated copper disc. So it was a copper disc, gold-plated, so both right. Yeah.
Yeah, so and that message is called Murmurs from Earth. And Carl Sagan, of course, is the architect of that, including that, just in case, who knows, at some point, it gives a stellar map of how to come back to Earth. If some alien race ever runs across these two, one of these spacecraft, then they would have a map back to the planet Earth. Yeah. Who knows? Could be a million years from now. Who knows?
Yeah, long time.
So tonight in this episode, we mostly want to focus on sort of the second part of 3 related episodes. This is the vastness of space and the problems of traveling through space. I talked a little bit about Voyager last week, how long it would take, and Jimmy covered some more distance in his introduction. Voyager 1's the fastest spacecraft we've ever launched. Now, there's been some that's been launched that were faster for a moment. The solar, what was that? We were talking about that the other day. There was a solar probe that was launched that was very fast. New Horizons was fast for its launch. Mm-hmm. Voyager picked up velocity by doing these slingshots around the gravitational well of Jupiter and Saturn. So anyway, it's moving something like 38,000 miles per hour. But even at that rate, which sounds very fast, if it were pointed to our nearest star, Alpha Centauri or Proxima Centauri, approximately 4.3 light years away, it would take that spacecraft 70,000 years to reach that star. So we want to essentially discuss, and again, this idea of the difficulty of space travel. Like maybe that's why we haven't seen aliens. The Fermi paradox of where is everyone? Why is that? And the first thing you have to look at is the vastness of space. And I think, Jimmy, you have a pretty good analysis of that, right?
Yeah, well, what I did is I went to find an expert. Who I found was Dr. William P. Blair. He's an astrophysicist and a research professor for the Department of Physics and Astronomy at the Johns Hopkins University. And he wrote up a really good paper that scaled down our solar system and then our closest neighbor, our closest star, Proxima Centauri. It's part of a 3-group of star, which is the Alpha Centauri group. This is a really good breakdown of it and gives you an idea to sort of understand the vastness between just us and our closest neighbor, as well as all of the different planets in our solar system. So he says, imagine the sun is a ball that is 12 inches in diameter. And we're going to start.
What's up with you and 12 inches tonight?
I have aspirations, my friend. So, and we'll talk about that a little bit more when we get to the health side of things. Because they're doing genetic engineering for astronauts, and I can see the future. So anyway, let's say you have a 12-inch sun, a ball that is 12 inches in diameter. And we're going to call that the sun, and we're going to place it in Baltimore, Maryland. And there's a reason for that. And then we're going to look at Mercury. Now, Mercury, the diameter of it would be about 0.05 inches, essentially a grain of sand. And it would be 41.5 feet from the sun. Now, this is scaling everything down based on a 12-inch sun. Venus would be 0.11 inches in diameter, and it would be 76 feet, almost double the distance, not quite, of Venus to the sun. Mercury is to the sun. And then we have Earth, and we'd be at 106 feet, so a little bit more. We're getting out there a little bit. Then we've got Mars. It'd be 163 feet away from the sun. And then Jupiter would be 552 feet.
And I think that's one to think about. Once we go from the inner planets to the outer planets, these distances really start to spread out in our solar system. Yeah, so we go from Mercury at
41 feet.
41 feet from the sun.
We don't quite double that. We get Venus.
Yeah.
And then
76 feet from the sun.
Yeah.
The Earth 106 feet. Mars 160 feet. And then you go to Jupiter. You start getting to the outer planets, 500 and some feet.
And then we double that to get to Saturn, 1,012 feet from the sun. And then to get to Pluto, it's 4,200 feet.
Much, much, much further away from the sun.
Yeah, 0.8 miles. And then we get to our nearest star, which is Proxima Centauri. It's a little bit under 4.3 light years away. And it would be 5,680 miles. That's roughly the distance from Baltimore, where we placed our sun, to Hawaii.
And imagine the Earth would be a speck, a grain, not even a speck or a grain.
It'd be a small pebble.
That's just one illustration. That's our nearest star at only 4 light years away. Again, a light year is the amount of distance that it takes light to travel. The light you're seeing from that star system is 4.3 years old. Every time you look out into space, in fact, when you look at the sun, it's 8 light minutes away. So every time you see the sun come up, that light is 8 minutes old. It took the light from the sun 8 minutes to reach us.
Yeah, it blows your mind because the sun is not where you're seeing it. It's 8 minutes. It's 8 minutes in a different direction.
And when we start looking at these distances, I mean, still we're looking at our solar system. We're looking at feet. The inner solar system. I mean, which of course an astronomical unit is 93 million miles from Earth to the sun. So 93 million miles in this illustration. Imagine that being 106 feet, 93 million miles. And now the nearest star system is in Hawaii from Baltimore. It is an enormous distance, We can't fathom how to travel that far.
Yeah, so I was thinking about this, right? So if you keep with that scale, you make your little spaceship, right? Let's make it big. Let's make it like 5 times the size of the space shuttle. Okay, let's say that's our spaceship. Now, compared to a pebble, if you're going to scale that down, that's like smaller than a grain of sand. It's itty bitty. Now you got to fill it up with fuel that gets it from Baltimore to Hawaii, something the size of a grain of sand. Look how little that fuel is that you're putting into that ship. And then it's got to make it that distance. So
yeah, I mean, it's mind-blowing. So these are the problems. This is just one of the problems. The space is enormous. That's our closest star.
Yeah.
I mean, we want to start looking at just things that are close to us. Sirius, which is the brightest star in our sky, is something like 8.8 light years away. It's twice the distance. What is Wolf 359? That's the nearest star that we can see in the northern hemisphere. Unfortunately, if you're into astronomy and looking through your telescope, you can't see Alpha Centauri because it's in the southern hemisphere. But the nearest one we can see is Wolf 359, and Wolf 359 is a red dwarf. It's 7.9 light years from Earth. So we're talking about almost twice the distance. And so if we're really talking about interstellar travel and exploration and just the way you imagine it on television or whatever, it's just not going to exist that way. And there's some other problems that we will run into.
I looked up some of the spacecraft that we have launched, and it gives you a breakdown of the speeds that they travel, and then, how long it would take them to reach Proxima Centauri. And it's mind-boggling. So the New Horizons is, its top speed, I guess, was 52,000 miles an hour at its peak, and it would take 54,000 years to reach Proxima Centauri. NASA's Juno traveled at 165,000 miles an hour, and it would take 17,000 years. And that's what it was at its fastest. The Parker Solar Probe traveled 163 kilometers a second. That's the one that went into the sun, and that was because the sun pulled it in. It would take 7,000 years for that, the fastest thing that we've made, and the only reason it was that fast was because the sun pulled it in. Now, we have a new project that's supposed to be launched sometime in the future, near future, I think. It's called the Breakthrough Slingshot Initiative. And that is this solar cell that contains a wafer chip in it. And the idea there is that they'll have this large solar cell. It would be a really thin material. And then we would use a bank of lasers on ground on Earth to fire off at it and accelerate it out of our solar system toward Proxima Centauri, and it would reach speeds up to 20% the speed of light, and that would take 20 years to reach Proxima Centauri.
Yeah, that reminds me of The Mote in God's Eye, the Larry Niven novel.
That's a great novel, and that's the first time I heard about a solar cell.
Yeah. That's how that I can't remember the name of the alien race that first traveled into
the Brownies or something.
The rest of human space was using a solar cell, and they called it the Mote in God's Eye because whatever that red light that was the laser being projecting it, that craft into the nearest star system. Yeah, that was pretty cool. It's been many, many years since I read that. But very cool story. Yeah, and we'll get into a little bit more about some of the technologies next week when we start talking about that. But the main thing we need to impart here is just the vastness of space. And yeah, there are going to be some technologies to come along, and there are some ideas that can come along that may allow us to reach out to our nearest stars. But are we ever going to have a situation like Star Wars or Star Trek, where we can hop in our spaceship and go into hyperspace, and a few hours later we're at some other star system across on the other side of the galaxy, or hit our warp drive and be there in a matter of a day or two? Are we going to have that? I don't know, because when we look at the technology, we think about where we are right now, and we're putting a lot of emphasis on what we've launched now. What can we launch 200 years from now? I mean, 200 years ago, the fastest human was however fast a horse could ride, or however fast a sailing ship could go, right? Maybe 40 or 50 miles an hour. Well, I don't even think that fast. And then along came the railroads, and people started moving quicker than that. And there were physicists at the time, or scientists at the time, that said, the human body can't sustain these speeds of more than 30 miles an hour or 40 miles an hour. And then, obviously we can. We have people who are in spacecraft right now traveling much faster than that. And people routinely board commercial airliners, millions of passengers a year, and are going hundreds of miles an hour to their destination. I mean, what would that have looked like to your average person from the 18th century?
We consistently, as a species, make the impossible possible with each subsequent generation.
Yeah, so who knows? But there are some laws of physics, though, that we need to talk about. The mainly what we need to discuss is relativity. There was two theories of relativity as they're known today: special relativity and general relativity. Albert Einstein published special relativity in 1905 and later published general relativity. And it changed the way all scientists, physicists looked at the world, because it laid out laws of physics. In fact, when he did the mathematics, there were things and implications of the math that he didn't even understand, that Albert Einstein didn't understand necessarily. He didn't, but it took other scientists and other mathematicians doing the calculations and thinking about these concepts, understanding that, hey, like for instance, that space is expanding. Einstein himself, like most scientists of his day, believed that the universe was static and infinite, and that it had always existed and it always would exist, right? That it was this static, infinite universe. Using his mathematics, can't remember the name of the scientist, it was a Jesuit priest, I think, who also was a physicist, who approached him at a science conference, Einstein himself, and said, your mathematics point to an expanding universe, a universe in motion. And even Einstein himself just did not like the idea. He hated the idea. And then after a few years, Edwin Hubble, who had already proved that the Andromeda galaxy, which some astronomers back in those days in the 1920s believed that the universe, or that the Milky Way galaxy was all there was, and the other galaxies you could see, like Andromeda, were nebula, like cloudy, nebula. Edwin Hubble was the first one to prove Andromeda was actually a galaxy. It's 2.5 million light years away. And then, of course, after that, they discovered other galaxies. Edwin Hubble, he started looking at the motions of all of the galaxies that he could find, discovered that the universe indeed was expanding. And so, Einstein had at first hated the idea, but his own laws illustrated a lot of these things that only come to be found out to be true many years later. For instance, things like black holes, which weren't discovered until the 1960s, pulsars, gravitational waves was something predicted by Einstein's theories, and they were only confirmed in 2016. So for our conversation today, anytime we talk about relativity, right, what it really means is relative to what? So when we talk about motion or anything, that's in a sense why it's relativity. It's relative to what? For instance, if you place a ball, Jimmy's 12-inch ball, let's say, and you place it on a table, in the center of a table, you may look at that and you say, that ball is at rest. It is not moving. Then you look out a window and you see a car go by. That car is moving. A car is moving relative to what? To me, as I'm stationary looking out the window, to the ball, which is stationary on the table, right? But in reality, everything is in motion. The earth is in motion. You're in motion all the time. And just to give you some other figures to kind of put these things in perspective, the earth is always rotating. The sun coming up, setting every day. It's an illusion of the earth rotating. And our perspective of it as the light from the sun reaches the earth as it rotates toward the sun and sets in the west as it rotates around into the shadow. So the surface of the earth at the equator moves at 460 meters per second, or roughly 1,000 miles an hour. So just the rotation of the earth is 1,000 miles an hour. So think about that. You're rotating on the earth right now, wherever you are, at 1,000 miles per hour. Then the earth, of course, throughout its seasons is doing a revolution around the sun. It's moving around the sun like all of the planets do. And the speed at which it does that is 30 kilometers per second, or 67,000 miles per hour, is how fast the earth is moving around the sun.
Yeah, you're freaking me out a little bit.
And just the last one I'm going to say is the earth, our solar system, is moving around the center of the galaxy at 220,000 kilometers per second, or 490,000 miles per hour. So we're already moving at 500,000 miles per hour.
So you literally can't drive 55.
Right. I mean, you're adding your 55 miles an hour onto these other relative speeds, right? So that's what relativity really means. But in a much more complex way about other observable things. But, you know, think about that. We're already, I mean, our solar system is moving much faster than any of those probes we talked about that were launched. But that's their velocity relative to us and their velocity, what's been added to their velocity, right? And that's what led Einstein to think about the speed of light itself. We're all moving. So can you add anything to the speed of light? You know, it's kind of like that old joke. If you were moving at the speed of light and you turned your lights on, what would happen? Well, nothing, because nothing can move faster than the speed of light. You can't add the speed of light to your velocity. It always moves at a finite speed. Doesn't matter how fast you're moving. We can be moving at these velocities, or the New Horizons probe. The light that leaves that bounces off that and leaves that, is always moving at a constant rate. It's really the only constant in the universe that we know of.
Well, as far as we know.
So what does all that mean?
I don't know.
When it you know, like I said, I don't want to get too deep into the weeds. What we know as a law of physics is that nothing can move faster than the speed of light. Nothing in the universe can move at or faster than the speed of light. There's nothing to say you can't move 99.9% the speed of light if you have enough energy to get there, but nothing can exceed the speed of light. So that is always going to be a limitation unless somehow we find a way around that. But it's not just like an engineering problem. It's not like we need to build a faster rocket. We need to build a faster spacecraft. We need, you know, a better engine to push us. Nothing can push us through normal space as we understand it past the speed of light. So that will always be a limitation.
Yeah. I know you didn't want to get too much into the weeds there, but I already feel like a rabbit in the Serengeti. I can't see anything through all of the brush. Yeah, it's a little hard to wrap your mind around. I sort of came up with a thought experiment to address just getting from Earth to Proxima Centauri using a spaceship that we designed with our current technology. And that thought experiment helped me understand a little bit better of the challenges we have to overcome right now with the technology level we have. I mean, we're going to be talking about future tech in the next episode, but for the technology we have now, it illustrates some of the problems we have, and maybe future tech will solve those. Obviously, it will, if we're able to start transversing the galaxy. But there were two categories I found beyond the distance problem, which we've already talked about. The first is transversing the interstellar medium, and the other is us as human beings and the problems we have operating in space, and how space just beats the crap out of our bodies, and the things we have to do to overcome that aspect of our biologies, having grown up in a gravity well, being able to survive in a microgravity or a zero gravity, that causes all kinds of problems. So we'll tackle each one of those independently. And we'll start with the interstellar medium. Yeah, so interstellar medium refers to all of the crap that exists out there in between stars. So we've got our star, the sun, and then we've got the star in Proxima Centauri. And in between there, we've got to travel that distance, and we're going to hit a bunch of crap along the way. Now, the interstellar medium is primarily made up of gases. It's about 99% of its gases, and then 1% of it is dust, interstellar dust. And a typical dust grain consists of a core. It's a rock-like material, silicates, or graphite, surrounded by a mantle of ices, water, methane, ammonia, most likely. Those things are really, really small. They're less than a grain of sand. They're not very big. The gas particles themselves, obviously being gases, they're made up mostly of hydrogen and helium. And this is what we have out in space. Now, the problem comes when we start trying to traverse that distance at a very fast rate of speed. So if we get up to 20% of the speed of light, and we start hitting some of these larger particles, the speed at which we're going and hitting those particles, as small as they are, they'll disintegrate the front of the ship. It's almost like being in re-entry into Earth's atmosphere. Imagine going much, much, much faster into the atmosphere. While the atmosphere is more dense than interstellar space, it doesn't take much to start eating away at the ship hull. And over 4.2 or 3 light years, you're going to hit a lot of crap in there. Even though it's very diffused, you're still going to hit a lot of stuff. So that's one problem. So we've got to come up with a shield. Now, there was a paper written in about 2016 that identified about the size of shield you would need. And it's not very thick. It's titanium, and a couple of millimeters would probably do it to get us to Proxima Centauri. Now, that takes care of one problem, but the other problem we have is the speed at which hydrogen or helium hits the ship, even the shielded ship. It strips away electrons and releases radiation, essentially, in the particles that remain. So now you have radiation bombarding the ship. So you have to have a second layer, usually of lead is what they're thinking. So that'd be your second shield. And then you've got another problem in cosmic radiation. Now, cosmic radiation is going to be hitting you from all sides, not just from the front. So that means your whole ship has to be shielded so that you're not going to be bombarded with cosmic radiation. So if you're able to overcome all of those things, then you're able to get across that large chasm to Proxima Centauri in one piece. But those are some of the challenges you have in the interstellar medium.
And then, of course, one big challenge that we're already facing in space travel today, I mean, even looking at a trip to Mars or a long-term moon base, the sort of things they deal with on the International Space Station is being in a weightless environment is not very healthy. Of course, you're always being exposed to radiation. Yeah, I mean, astronauts take the risk. They know the risk that they're being exposed to higher levels of radiation than under the protective cover of our atmosphere and also the magnetosphere around the Earth. When you get out away from the Earth and you start traveling through space, you're going to have to deal with that. And especially the microgravity could be a real problem. And that could be a problem with us even colonizing our solar system, which inevitably I think would be the first. If we leave Earth and begin to live in space, it would make sense that we would be on stations or possibly the moon. We would just have to deal with that. I mean, could we even reproduce in microgravity? I mean, some people believe that like 1/3 gravity would be enough. I mean, it certainly would change the way human beings looked. They would just evolve a little differently though over time. I mean, the novel series, The Expanse, that later became a TV show, they hypothesized that the people that were belters that grew up in space and generations living in space would be really tall and thin, have elongated bones, and would actually, it would be painful for them to return to Earth and almost fatal to return to Earth. And even people that grew up on Mars wouldn't be used to the heavy Earth gravity that, of course, us Earthlings live in every day. that would be a problem.
Yeah, so we have some good science behind this. There's a paper written in 1994 by Melishkov, Shepilov, Avner, and Volk. And they break down some of this, like you were talking about, the impact of microgravity on sexual reproduction, for example. They even did something on that. So gametes, which is sexual sperm, female egg. So the exposure to radiation at levels as low as 10 rem has been known to cause reduced levels of sperm production, and exposure to levels of 50 rem may cause temporary sterility. So, I mean, astronauts are risking it all up there. So, yeah. I'm just saying that.
I mean, they're risking cancer, sterility. I mean, they know the risks now. I mean, our early astronauts didn't know.
Yeah.
But they know the risks now. They know the risks now about a mission to Mars. We have plenty of volunteers that would go on this mission. But
you know, one good thing, though, if you're up there, you can grow. You get taller. I could grow 12 inches if I were in space. Now, one astronaut did grow, like they measured one astronaut, he grew an inch while in there, right, because the spine on Earth is compressed by gravity. Out in space, it's not so. It means now one thing they did find with astronauts, they tend to have a higher level of herniated disc. And there's a whole list. So let me read just a few of them. So astronauts, I mean, they're really risking stuff here. So one thing they found is there's sort of, you know how you have seasickness? They have a space sickness that they get. They call it space adaptation sickness. The first few days that you're in microgravity or low gravity, you get this almost like seasickness feeling as your body is trying to acclimate to this new environment. And then your vision is screwed up, and sometimes that lasts for a while, and I don't know how long it lasts. Some people regain their vision, but some of them don't, I guess. The eye problems caused by fluid around the optical orb, because what happens is the blood in your body actually piles up in your chest and in your face, and you'll see the astronauts, they'll get puffy in the face because more of their fluid is in the upper part of their body. They also have 1 to 2% loss of bone density. They also have muscle loss, so they'll do exercises, and they've built special equipment on the space station, for example, just so they can try to keep as much muscle mass up as they possibly can, so that when they return to Earth, they'll be able to, better make that transition back into a gravity well.
I remember one of the Russian cosmonauts, I think, back in the Mir days during the Cold War, the Russians were really big on setting the longest time in space. And one of the Russian cosmonauts was up there a long time. I don't know what the record is. I know it's over a year. I mean, it's a long time to be in orbit in a tin can orbiting the Earth. But I can remember this one particular guy just saying that having to get up every day and exercise, it just became like almost unbearable, that he had to try and keep his but it just became so hard to live there and to exercise so much every day just to try and keep his body in some kind of shape when he returned to Earth. Yeah, it's not a good environment. And, I think, too, we're going to see, right now we have plenty of adventurous souls that want to go to Mars, go wherever, go back to the moon. But they get to go out there, even to Mars. It would be very dangerous and very long and difficult mission. But they're probably going to be back home in 2.5 years, right? 3 years maybe. But, what about Elon Musk and people like that says we're going to colonize Mars, in 100 years? Who would want to live there? I mean, really. I mean, it would be great to go there and the adventure, the exploration, go out and explore. But then all of a sudden, what if you were a colonist and you couldn't come back to Earth? It would be a very unpleasant place to live. I mean, you would have to live inside. Couldn't go outside without a vacuum suit on. It was just constant danger of being in a hostile environment, or if you colonize space. And then who knows what it would do to your body, being exposed to the radiation, being exposed to microgravity like that. I don't know. I think it'll be hard to colonize places like that.
I hear if you get on Twitter, there's a lot of people say, I'm done with this planet. I'm ready to leave. So those people can go.
Yeah, speaking of Elon Musk. So those are some things to think about. Any space journey is always going to be filled with that. And of course, an interstellar journey. would take many years. Obviously, any interstellar journey would be made first by robotic probes because they can handle all that, no problem. But our communication with those probes would be extended the further they got away from Earth, because if they're halfway there, it takes 2 years. You know, they're halfway to Alpha Centauri. 2 years for them to reach a message from us at the speed of light. And then 2 more years for us to receive it. They're already going to be there by the time we receive a message from halfway there, right? Or a response to the thing we sent. So it would have to be a really very autonomous equipment to be able to, because we don't really know what's there, right? Can't see with that kind of detail. But just, there's another piece I want to touch on. So that's, we have the cosmic speed limit. This is back on relativity, some of the issues. So special relativity, a couple of things. I'm going to leave some of these out. They're irrelevant to our discussion. But the maximum speed limit, the speed of light, E equals mc squared. This is the famous equation when we talk about relativity, right? Everyone has seen this. Probably the most famous equation in history. E equals mc squared means that mass and energy are interchangeable. And of course, the discovery of this led to nuclear power, nuclear bombs.
Thanks, Einstein.
Right. So energy and mass are equivalent and transmutable. Of course, that's exciting. One of these days, we may be able to turn energy into mass. Be like the, what do they call them in Star Trek? Replicators in Star Trek. That's the premise there, is you're taking energy,
changing it into a steak.
Making chicken noodle soup, right?
a boxed wine.
Or what is it? What's the tea? Gray something?
Earl Grey.
Earl Grey.
Yeah.
Hot.
Pickard.
Yeah.
John Luck Pickard.
Another issue about traveling in space that we have to talk about, and that's time dilation. So this is something that is a real thing.
I got a question for you. On this front, I got a question for you. And I don't know if you can answer this, but something we probably need to find the answer to. So let's say I'm getting on the spaceship and you're staying here holding down the fort with the podcast, right? And I get on the ship and I travel to Proxima Centauri, and I travel back in my little spaceship at, let's say, 20% the speed of light. Let's say I'm a fancy ship. I'm able to do the speed of light, or damn near 99%. And I travel there and I come back. Am I doing the podcast solo because one of us is dead, or are you doing it solo? How does that work? Because I heard this thing about the twin paradox, where, you know, you got twins and one goes out in space, like travel speed of light, and then comes back. And when he gets back, his twin's dead, and, you know, he's going, ha ha.
Right.
Yeah. Okay, how's that work?
So that's something very important. So that's another thing we learned with relativity, is that time passes differently depending on your velocity, your speed. Now, as we stated earlier, we're already moving pretty fast through the universe. But when we start talking about trying to explore the stars, then we're going to have to move at much faster velocities than that. And so that will cause, from the perception of someone on Earth, Jimmy jumping in his spaceship, time will move slower for him relative to me. And another thing that affects time is gravity. The movie Interstellar explores this quite a lot. When you get down in the gravity well, time also slows down for you than if you're not in that gravity well. This is something we have to deal with our GPS satellites. They have to be realigned every so often because of this. There's a couple of what's called like space travel calculators and things on the internet. You could look this stuff.
Ooh.
Okay. And it's a fun way to look at space travel and put things in perspective. So your question is, you're going to travel to Alpha Centauri, and we've been using Alpha Centauri, Proxima Centauri kind of as a
ballpark
interchangeable. It's a triple star system.
Yeah.
Proxima's slightly closer. I don't know. I like saying Alpha better.
I do too. It sounds like Alpha Dog, the number one.
Yeah, maybe that's it.
Yeah.
So anyway, this time dilation in respect to space travel. So we have these. You can find these on the web. Just pull up like space travel calculator, something like that. Mm-hmm. And there's some are better than others, but here's one that, let's say Jimmy hops in his spaceship.
Yep.
He's going to travel to Proxima Centauri. Well, let's say Alpha Centauri.
Sure.
It's already
like it better.
I already have this loaded.
Perfect.
4.37 light years away. Now, he's going to accelerate at 1G. Jimmy has an antimatter power source or something like that. He's using like a photon drive. It's doing something that can continually accelerate at 1G. That way he can, under that acceleration, he can feel like he's on Earth, right? 1 gravity, that means 1G.
All right.
So he's going to accelerate at 1G acceleration.
Okay.
Halfway there, he's going to flip his spaceship around, and he's going to decelerate at 1G.
Yeah, so I can slow down.
So halfway there, he's going to be going as fast as he can go, and then he's going to flip around, and he's going to decelerate. So, Jimmy, I made your spaceship 10 tons.
Fair enough.
I figure you need some cool stuff on there. You need some of that shielding we talked about.
Need a pool table.
Your maximum velocity accelerating and then decelerating at 1G.
Yep.
Gets you to 0.95% of the speed of light.
Kick ass.
When Jimmy reaches out to me, of course, I have to wait for his signal to get here, but time that passed on Earth for me is 6 years, but only 3.58 years have passed for Jimmy.
Oh, wow.
Yeah.
That's a good deal.
Just in that short, yeah.
For me.
Not bad.
Yeah.
Now, let's say that Jimmy wants to go to Sirius. That's our brightest star. It's pretty cool. It's about 8.6 light years away. Now, that's going to take Jimmy, from my perspective, Jimmy's going to get there in about 10 years. But Jimmy gets there in 4.6 years on space time. So in ship time, it's a long journey, 4.6 years. But for me, it would be 10.35. So in other words, if Jimmy went to Sirius, checked it out, took a couple of pictures, and came back, it would take him
8 years?
About 9 years.
9 years.
Right?
And take
to
you
get there and back.
And 20 years.
But 20 years has passed on Earth.
So for both podcasting, you will have done 20 years of podcast, and I will have done 9.
Right. Remotely. I'm liking this deal. It's working out good for me. Because you're almost traveling at the speed of light. At this point, accelerating at 1G, you would reach 0.982% of the speed of light.
So if you wanted to live forever, you set up a company on Earth to start doing genetic research on how to extend human life, and then you fly on in a spaceship near the speed of light and then come back. And every 10 years or so, you check up on people and say, how's it going?
Yeah.
How much things? Oh, you figure stuff out. Okay, hit me with the treatment. I'm going to go back out until you get it better. And you keep doing that until they get it to a point where you're immortal, and then Bob's your uncle.
You would have time. Because, Jimmy, if you hopped on your spaceship and you thought, you know what I really want to see,
and I would.
Anything else?
I would.
I want to see Betelgeuse.
Oh, yeah.
I want to see that crazy star.
Betelgeuse. Yep.
Exactly. I mean, I would want to check it out as long as it wasn't getting ready to go supernova. Right.
Hell yeah.
So you're lucky it would show up about the time that it
blew.
Would annihilate anything within about 100 light years around it. But
oh man.
But anyway, Jimmy, you could hop on your spaceship. You could be there in 12.6 years. I mean, it's a long time.
No way.
12.6 years. But you know how much time would pass on Earth?
12.7.
Well, you travel to Betelgeuse.
30 years?
You travel to Betelgeuse.
Yeah.
Right?
12 years.
If you had some way to instantaneously trying to call me, I would be long, long dead because 640 years have passed on Earth.
Holy crap, that's a bad deal for you.
Well, I mean, I'm still living my life, but you know, you're a time traveler, and that's the only way you can really travel to the future in a way. But if you were able to accelerate almost to the speed of light.
Yeah. What if I make it there, and then I find out that they figured out how to put heads in floating fish tanks like they do in the Futurama, and you're now a head in floating. That could happen.
That would be cool. Yeah, that would
be way cool.
So anyway, I'm going to drop back to Alpha Centauri real quick because I want to point out one major problem, and this is a major problem that everyone talks about. So let's assume this is a fusion power plant, right?
Yeah.
In other words, you're just getting hydrogen. Now, we're going to talk a little bit more about this next week, but the only problem about you traveling at 0.95% of the speed of light going to Alpha Centauri, ship time 3.5 years. Your 10-ton ship would require 392, almost 393 tons of fuel. And that's the problem we always run into. Unless we can come up with some, that's if you were burning hydrogen. If you're fusing hydrogen into helium, not really burning it, but fusing it in a fusion reactor of some type, or had a fusion drive. That's a generous amount of fuel. If that was a chemical rocket, forget about it. You'd never get there.
Yeah.
So that's a problem that all scientists see right now, is the amount of fuel that it would require, even using something very efficient like fusion. I mean, maybe some type of antimatter drive, if somehow. I mean, there's been experimentation in antimatter now. So maybe someday.
Now, does that fuel take into account the weight of the fuel itself? So you need that fuel for the.
You mean of the ship? Of course not.
Yeah. So you need more fuel because of the fuel that you have when you're starting out, and as you use it up,
that's the problem.
Yeah, and
you can never
you can never have enough fuel.
You can never take enough fuel with you to make the journey to start
because the fuel weighs more, and then you need more for that fuel, and then yeah.
But now when we want to start talking about traveling at what would still be considered a relativistic speed, 10% of the speed of light, 20% the speed of light, something like that, we could still, now that they're doable, and we'll talk about that next week. We don't want to go too far.
Yeah, don't jump the gun.
The main thing we wanted to emphasize tonight when we're talking about the problems of space travel is the vastness of space itself, the limitations that, according to the laws of physics, the speed of light and time dilation would have upon anyone, any civilization wanting to explore their nearby stars. These are real issues. No matter what level your technology is, time dilation will never go away. And these distances, but again, who knows, 200 years from now, 500 years from now, 1,000,000 years from now, who knows what technology will be developed. But that's the kind of stuff we're going to talk about next week. The best way we can understand it, or maybe how we could reach out to the stars in the next, say, 100 years. What kind of technology can we foresee now, or what would it take?
Yeah, so I'm excited about that one.
Yeah, that's a pure speculation. I mean, this one is these are the facts. Now, how are we going to get around these laws of physics? How can we go to the stars, or how is some civilization? How could some civilization come to us and visit us? So we're going to look at all of that stuff next week. Jimmy, have anything you needed to add for tonight's episode?
Yeah, one more thing. I want to talk about mad scientist. So one of the problems we had with the health side of things was the cosmic radiation. So radiation, one of the major issues with space travel is going to be radiation. In orbit, we're outside of the protective shield of Earth, but we're still within the protective shield of the magnetosphere of Earth. So right there, it's about 10 times, the cosmic radiation is about 10 times what it is on the ground. When you go out away from the magnetosphere, it's even worse. So scientists, believe this or not, have you ever heard of a tardigrade?
Oh, yeah, those little tiny microscopic creatures that live on your body.
Yeah, they call them...
That's something else for you to think about when you didn't realize stuff was in your gut.
Right. A Wasserbär is what they're called in German. Wasserbär. And these Wasserbär are very resilient. They can be found in all kinds of environments on Earth, and even in outer space they can survive. So what they've done with these, they've discovered that they are very resilient to radiation. So this one scientist wants to start gene splicing the tardigrade into human cells and has done it in a petri dish. And human cells are able to survive 40% longer with the same level of radiation from one to the other. This researcher, what is his name? Because I'm going to out him here. His name is Chris Mason. He's a geneticist and associate professor of physiology and biophysics at Cornell University out of New York. And he believes that this DNA modification could help astronauts survive in space. He's proposed multiple approaches on how genetically engineering a person will be key for successful space missions to Mars and other distant worlds. So you can be half human and half Wasserbär and make it all the way to Mars.
Yeah, they've survived all 5 mass extinctions as well.
Wow.
Major mass extinctions. Yeah, they're
Suck
very,
on
very
that,
resilient.
cockroaches.
Yeah, that's right. Yeah, I mean, ethically, we could talk about this all night, but is genetic gene splicing inevitable? Probably. Will we someday tailor human beings to better live in particular environments? I could see that. I mean, I've read science fiction books for years about that sort of thing.
John
That
Scalzi, Old
all
Man's
about.
War. That's a great book, folks.
Genetically engineering a human in order to live in some type of hostile environment. I mean, think if we can travel to the stars someday and we go to a planet, but the gravity's different, or there, like, hey, we can terraform this, or we can live here on this planet, but human beings would die. The atmosphere is toxic or whatever. I could absolutely see that. In fact, I think that would almost be necessary. The chances of finding a perfect environment like Earth that we live on today, or the way Earth was 1,000 years ago or 10,000 years ago, highly, highly, highly unlikely. The chances of us finding another environment out there somewhere, even if we could travel like Star Wars and Star Trek, I mean, I don't know, just the same thing as the question with life, but I think it would be unlikely. I mean, the existence of the organisms on Earth itself have created this environment for us to thrive in, the interaction of all the organisms on Earth. The plants creating oxygen that we breathe. That's just one step. I mean, could we exist and survive on another planet? I don't know. But could we genetically modify human beings to live in many different environments, be able to withstand radiation, be able to live in microgravity? Probably.
Yeah.
So,
I'm all in. Hit me up with those water bear genes.
and by then we may be able to upload our consciousness into a Voyager spacecraft or something, right?
Yeah, like the Star Trek
There's your
movie.
there's your way to explore the universe, in a machine that could, what was it? The very first Star Trek movie,
Yeah.
Voyager, or whatever.
Voyager.
Voyager.
I don't know how to pronounce words. Call me Voyager.
I have all this massive, amazing technology, but yeah, I didn't know to rub a little dust off of the nameplate.
You come a long
All
way
right.
from 1977, Voyager.
Yeah, I like that movie. Most people don't, even Star Trek fans, but I don't know.
I'll like it when I finish watching it. I keep falling asleep.
Oh, I'm pretty forgiving when it comes to a lot of science fiction because, well, it used to be, it was so rare. Now with CGI, there's all kinds of science fiction, a lot of bad science fiction. But
Star Trek 1 was like that first movie was like, I don't know, an hour and 20 minutes of watching the Enterprise in dock.
yeah, there's a lot of that.
Yeah.
I agree with you. But I mean, look at 2001. We were talking about that before we got on tonight. I mean, that was like,
Well, that's where we
20
got
minutes of watching.
That's where we got the idea for Cosmic Sponge, the Cosmic Sponge thing.
Yeah, that's right.
Two monkeys, Steve and Jim, trying to touch the Cosmic Sponge monolith.
It's iconic. That is for sure. All right, man. Well, let's wrap it up here. Be sure to tune in next week. We're going to continue this. We'll wrap it up with some proposed ways to travel among the stars. But we mostly wanted to cover the problems, the difficulties that human beings would face today if we wanted to try and, or in the near future, to try and travel between the stars, and the kind of problems that another alien race would have to overcome. So next week, we're going to look at maybe solutions to some of these problems and what scientists have come up with. Before we get out of here, I'd like to remind everyone to please rate and review the podcast. It helps other people find the show. Look for us on Instagram and Facebook, YouTube.
Yep.
If you're listening to this on YouTube, you already know that. Go to our webpage, CosmicSponge.com. There you can find the web store and ways to support the show. Our contact information is firstcontact@CosmicSponge.com. Jimmy, did I leave anything out?
Nope. I think we got it all covered.
All right. With that being said, this is Stephen Hawk signing out, and we'll see you next week.
And Jimmy Coe, keep your eyes to the skies and your feet on the ground. Catch you next week. Hey, I'm looking at a picture of a tardigrade here. It's got a butthole for a face.
That it does.
Yeah, you know,
I remember.
I want to be.
Yeah,
Yeah, they say they're micro animals. guy who discovered them in 1777, an Italian biologist, Lazzaro Spallanzani.
He must have had hellacious eyesight. Man.
How did he see them? I don't know. They were first described by German zoologist Johann Augustus Ephraim Goaz in 1773, who called them kleine Wasserbär. And they've been found in diverse regions of Earth's biosphere. That's just pretty crazy, man. These little butt-faced critters.
I wonder if they're living in that poo library or
They're also called moss piglets. Moss piglets. Yeah, I want to be a moss piglet.
All right, man, let's get out of here.
Indeed. I'll catch you next week. That's all for this week's episode of Cosmic Sponge. Please don't forget to rate and review us wherever you listen. It helps others find the show. If you have any questions or have a story you'd like to share, you can contact us using our email account at firstcontact@cosmicsponge.com. If you'd like to support the show, consider becoming a Patreon at patreon.com/cosmicsponge, where you get access to exclusive content, including our Weird Wonders news and stories released every week. To explore everything Cosmic Sponge has to offer, including other ways to support the show, head on over to our website at www.cosmicsponge.com. Thanks again for listening, and we'll see you next week.